Well, hello, AP Calculus class. Today we're going to start a series of videos on some topics that we're just running a little short on time. If you look in your Google Classroom, you'll see that I have loaded a Chapter 8 notes and a Chapter 8 homework. So in this video, we'll be using both of those. So if you want to open up your Chapter 8 notes, we'll just go ahead and jump in and get started. Okay, so we're going to look at volume by cross sections today. And before I jump into the notes, let me just give you just a brief little introduction to what we're actually doing, okay? So what we're doing, so on the right here you'll see a 2D picture of it, and then on the left is a 3D picture. So in this particular case we have a function or even two functions, and we would be told that we're trying to find the volume of that solid, right, the solid that's formed using rectangular cross sections. So if we were to drop these two linear functions flat, it would look like this, and then the rectangle in a 3D version would look like this. So from a 2D version, we see the rectangle just looks kind of like this, right? So the idea is that if we string together enough rectangles here, right? If we string together enough rectangles and we find the volume of those rectangles, that we can find the volume of our solid. All right, so we have all these now the rectangles are going to have different sizes to them as we progress through the actual shape. Okay, I'm sorry, I'm not very good at drawing these, but do the best I can here. Okay, so what we're dealing with here, we have function, like maybe this might be your g of x is a linear function, and then maybe this is f of x. The solid formed here is, right, this is the solid formed right here, okay? So in this particular case, we're asked, see if I can erase that now. There we go. No. Guess it doesn't want to erase. Okay. In this particular case, we are asked to find the volume, and we're specifically instructed to use rectangles that are perpendicular to the x-axis. Okay. Here's another example down here. In this case, here's my two functions. I have x squared and I have 8 minus x squared. So I have two curves here, and they form a region, we'll call this region R, bound between the two curves, and we're asked to find the volume of that solid that's formed. And in this case, I'm asked to use semicircles. Well, of course, from a 2D perspective, it doesn't look any different, but if you were to drop it down flat, we're going to look at it like this. So what we're doing here is we're going to find all the semicircles here. Okay, now this will make more sense as we work through some examples. But if I were to string together basically an infinite number of semicircles, right? String together an infinite number of semicircles and find the volume of all of those, I'm going to find the volume of this solid region here. Okay. So that's basically what we're doing. Excuse me. In order to do that, we need to know some basic formulas. Most of them you're going to be fine with, but there are a couple, especially some of these triangle formulas, that we need to make sure we're familiar with. Okay. So, and for the purposes of our cross sections, okay, we're going to, instead of calling it a leg or a height, we're going to call it the base. Okay, so an isosceles right triangle that means that the two legs are the same. So we know the area of a triangle is 1/2 base times height. Well, in this case, the area of the triangle will be 1/2 base squared. Okay. And then if the right triangle has the hypotenuse as the base, and we'll do some of this so you'll know what we're talking about once we do it. We're going to use 1/4 base squared. And I don't want to take time to show you where that came from. So you could do it if you wanted to, if you just kind of use your Pythagorean theorem to find out what this other side is, and you could come up with this, okay? For an equilateral triangle, we're going to use the formula to square root of 3/4b squared. And of course, that's based off of the fact that these are all 60 degrees because it's equilateral, right? Area of a triangle is 1/2 the base times height, which means I'm looking at a 30, 60, 90 triangle. Okay, so that's where that formula comes from. But again, I don't really want to take the time to go through that with you, okay? So I'm just going to ask that you trust me on that. But you do need to know those formulas. We will use other formulas also, but they're formulas that you probably know. Okay, so let's jump in and let's look at this first example. It says, find the volume of the solid whose base is bounded by the function y equals the square root of x. Well, there's my y equals square root of x right there. And the line x equals 4, so that's right there, okay? So this is a solid. Each cross section is a square taken perpendicular to the x-axis, all right? So looking straight on, we're gonna be looking just basically something like that, right? Now, if I could manage to drop this down, I don't know if I'm going to be able to do this or not, but I'll try. Well, that doesn't make any sense, does it? That's exactly what's up there. Let me see. Oh, I know what I'll do. Instead of that, I'll just kind of draw it in here at an angle, right? So basically, just pretend that what we're doing is we're going to have a square, right? And we're going to have a whole bunch of squares in here, right? We'll have another square here, so there's going to be an infinite number of squares nested in here, okay? So I wish I could draw better. Let me try and do it this way. There we go. Okay, there's one square, and then here we'll change colors. Hello. Okay, here's another square. All right. Right, and we got another square. Okay, I think you're probably getting the idea now, all right? So we're going to have an infinite number of these squares, okay? Okay, so what we're basically going to do is we're going to integrate the area to get the volume, right? Remember, volume is basically area times that third dimension, all right? So if you look here, right, my area is my side times side, but then my third dimension, right, my third dimension is actually the dx, which is the width, just like when we did the rectangular approximations, right? When we did a left and the right Riemann sums, right? That third dimension, that width, right? That's the dx, okay? Okay, so what we're going to do okay, so this is a square. So the area of a square, right? The area of a square is side squared. In this case, we're going to call it b squared or base squared, okay? Well, let's just look at this again and let's figure out what the side is. So the side, or the base of the square, right? The base of the square is actually the distance from the x-axis to the curve, right? That's the base of our square. And the distance from the x-axis to the curve is y. So this is actually going to be y squared, okay? So our volume is going to be the integral of y, which is the square root of x squared dx. Now, what am I going to integrate from? Well, we're going from 0 to the line x equals 4, so from 0 to 4. Okay, because we're going to have an infinite number of squares embedded in there, and all of the squares, they're going to have different side lengths depending on where it is on the curve. Okay, so they're going to have different side lengths, and the length of that side is going to be dependent upon where it is, which means it's going to be the y value. Okay. All right, so if we integrate this, we're going to get the integral of x dx from 0 to 4, which gives us x squared over 2 from 0 to 4, which gives us 16 over 2 minus 0, which is 8. So the volume of that solid, using square cross sections perpendicular to the x-axis, is 8. Okay? We're going to do so many of these, you're going to be sick and tired of them. Okay, next one. Find the volume of the solid whose base is a region bounded by the circle. Okay, so there's my circle. X squared plus y squared equals 9. And the cross sections taken perpendicular to the x-axis are isosceles right triangles. Okay. Isosceles right triangles, so we looked at those up here, right? There's my isosceles right triangles, except that the hypotenuse is lying on the base of the circle, okay? So if you go back up here, just picture, right, this triangle here, this is what's lying on the base of the circle. Okay, so we've got that triangle right there, right? That's the hypotenuse. Okay, and we're going to have infinitely many of these going through the circle. Okay, and here's my right angle. So this is where knowing that formula right there is going to help us, right? Remember, volume is the integral of the area function. So the area equals 1/4 the base squared. So if we're looking at this, well, what is the base, right? So this one we have to do a little bit of algebra, okay? Right? Here's my triangle right here. So I'm looking for that base right there, okay? Well, I know from the x-axis to here can be found using the equation, right? But it would be found using the equation, right? The equation is x squared plus y squared equals 9. Basically, I have to solve for y. So y squared equals 9 minus x squared. So y equals the square root of 9 minus x squared. Now, we know that's plus or minus, but we're going to take care of that in a moment, okay? So this distance here from the x-axis to the top of the circle is the square root of 9 minus x squared. So how do I find the base of it, right? Well, it's a circle, so it's symmetric. So the base is actually going to be 2 times the square root of 9 minus x squared. Okay, so that takes care of that whole plus or minus thing there. Okay. Okay, except that I made a mistake here. This is 1/4, not 1/2. See that? I wasn't paying attention. 1/4. Okay. Okay, so we're going to integrate, right? A volume equals. We're integrating from -3 to 3. The area function, which is 1/4. The base is 2 square root of 9 minus x squared dx, which equals the integral from -3 to 3, 1/4 times 4. Now when I square the square root disappears. 9 minus x squared dx. Okay. Well, 1/4 times 4, they're going to cancel, so I've got the integral from -3 to 3 of 9 minus x squared dx. Okay, so the volume equals 9x minus x cubed over 3, going from -3 to 3. Which gives us 27 minus 27 over 3 minus -27 minus -27 over 3. Okay, and when we do all of that math, that comes out to be 36. Okay. So the trick to these problems is figuring out the base. Okay, let's look at number 3. We have the R is a region bounded, so here's R, right? It's R. R is a region bounded by the graphs x equals y squared and 9. Okay, now I don't get ahead of myself. Find the volume of the solid that has R as its base if every cross section by a plane perpendicular to the x-axis is a semicircle. Okay, so we're looking at semicircles here, right? Okay, so we're looking at all these, a bunch of semicircles, okay? Now, have you noticed, though, that it's listed as x equals y squared? And that's not typically how we graph something, right? So if it's x equals y squared, then that means y equals the square root of x. That's how we would typically square it, and it would be a plus or minus, okay? So the area of a semicircle is 1/2 pi r squared. Okay, so let's think that through a minute, right? So in this case, what would our r be, right? So here's my semicircle here. Right, there's the semicircle. So if you look at that, you can see that r is going from the x-axis up to the curve itself. So r is actually the square root of x, right? This curve represents the square root of x. Okay, so the area function is going to be 1/2 pi square root of x squared, or 1/2 pi times x, all right? So our volume is the integral from 0 to 9 of the area function, which will be 1/2 pi x dx. Okay, so when we're integrating, if we have constants, we can bring them in front, right? 1/2 pi times the integral from 0 to 9 of x dx, which equals 1/2 pi times x squared over 2, evaluated from 0 to 9. Okay, now I'm not going to take up time stepping through this, but this will end up equaling 81/4 pi. Okay, I'm going to save some time by not going through the integration process, okay? Okay, let's look at example 4. Find the volume of the solid whose base is a region bounded by the lines x plus 2y equals 6, x equals 0, and y equals 0. Well, x equals 0 and y equals 0, those are the x and y axis. Okay, so let me just graph this line, right? X plus 2y equals 6. If I put that in slope-intercept form, actually I don't have to do that. I can leave it in this form and graph it by the x and y axis, right? So that means it's going to cross the x-axis at 6, right here, and it's going to cross the y-axis at 3. Right there, okay? Okay. So the region that we're talking about is right in here, this little triangular region, bound by that line, x equals 0, which is the y-axis, y equals 0, which is the x-axis. So we're talking about that region. They're cross sections that are perpendicular to the y-axis are equilateral triangles. Okay, so this time I'm looking at triangles that are going like this. Okay. So this time we're perpendicular to the y-axis. On these, we were perpendicular to the x-axis. Okay. Okay, so that means when I differentiate, it's going to be a dy. So my equation has to be y. Okay, so that means that I'm going to solve this for x. X equals 6 minus 2y. Okay. All right, so now the area of an equilateral triangle right? If you remember, up here was square root of 3 over 4 times base squared. Okay, square root of 3 over 4 times the base squared. Now the base is what I have to figure out, right? Is that gonna let me do that? Okay. Right, the base is what I have to figure out. So if we look at our triangle, the base, right, here's my base. The base is going, what, from the y-axis to here, right? That's the x distance. The base is the x value, right? So for the base, we're going to use 6 minus 2y, right? Because x equals 6 minus 2y. See, in these problems, we were looking at the y value, right, from the axis to the y value. So in general, right, if our base is going up and down, then it's the y equals that we're using. If our base is going left and right, just like the x-axis, then it's the x value that we're using, okay? Okay, so my volume is the integral of the area function. Oops, this is going to be dy, not dx. Okay. The integral of the area function, dy. Okay, now we're talking about the y-axis this time. All of our triangles are nesting, or we're summing them all together, but we're going along the y-axis. So we're integrating from 0 to 3, right? Because it crosses the y-axis at 3, right? And we're looking at square root of 3 over 4 base squared. So that's 6 minus 2y squared dy. Okay. So now we can bring the square root of 3 over 4 out. 0 to 3, okay? And that's going to be 6 minus 2y squared dy. I'm going to go ahead and expand that. So that'll be the square root of 3 over 4 times the integral of 0 to 3 of 36 minus 12y minus 12y, so that'll be minus 24y, plus 4y squared dy. Okay, when I integrate that, that'll be the square root of 3 over 4 make sure I get this right, and that's going to end up being, I'll write it out. Let me do it this way. 36y minus 24y squared over 2, so that's 12y squared, plus 4y to the third over 3, and that's evaluated from 0 to 3. Okay, so that will equal the square root of 3 over 4 times, 36 times 3 is 108, minus 12 times 9, which is 108, plus 4/3 times 27, minus 0, which end up being the square root of 3 over 4. 4/3 times 27 is 36. Okay, so that ends up being 9 square root of 3. Okay, so when it's perpendicular to the y-axis, we have to use the y values. If it's perpendicular to the x-axis, we use x. Okay. Okay, we're going to skip over to the homework. So let's go to Google Classroom and let's open up our homework. Okay. Okay, let's see, I need to download that. Let me just pause this while I pull it up, I guess. Okay, so now that we have our homework open, let's go ahead and scroll down to homework 8.5. And I'm going to try to save time by not actually stepping through the integration. I'll set it up for you, and then we'll look at the actual solution, okay? Okay, so this first question, it's actually 4 questions based off the same equation. Find the volume of the solid whose base is bounded by this. This is a circle, so we should recognize that as a circle, okay? So if we graph that circle, okay, it's got a radius of 2, centered at the origin. Okay. Again, forgive me for being pretty clumsy with this. Okay, so there's my circle, okay? And we have cross sections that are perpendicular with the x-axis, so that's great. Okay, so the first cross section is going to be a square, okay? So we're looking at a square cross section perpendicular with the x-axis. Okay. So we're looking at something like that, okay? Okay, so I can see that in order to do that, I'm going to have to solve this x squared plus y squared equals 4. We're going to have to solve for y, right? So that means that y squared equals 4 minus x squared. So y equals the square root of 4 minus x squared, okay? Okay, now a square is side squared, right? So the area of a square is side squared. Well, somehow I have to figure out the length of this side, right? So the full side of the square, right? So if I go from the x-axis up to here, that's just based on the y value or the function, right? So that part right there, that's going to be the square root of 4 minus x squared. But I need this part also down here. Well, a circle is symmetric, so it's the same distance. So the whole side of this square is going to be 2 times that value. Okay, so my area is actually 2 times the square root of 4 minus x squared squared. Because your area function is the side squared. So find that area function first. Then we have to figure out the base. Where am I getting the base from? And this base is the side of a square. Okay, so now let's go back and let's finish our integration, right? Volume equals the integral. Or where are we going? We're going, this is perpendicular to the x-axis, so we're doing the x values, -2 to 2. So we're integrating from -2 to 2. The area function, which is 2 square root of 4 minus x squared dx. That equals -2 to 2. Oh, squared, sorry about that. We're going to square the 2, which gives us 4. And when I square the square root disappears. Dx. Okay, so we can bring this 4 out. So that's 4 square root of -2 to 2, 4 minus x squared dx. Now when I integrate from -2 to 2, 4 minus x squared, I get 32 over 3. So multiplying that times 4, we get 128 over 3. Okay. Okay, let's do the same thing again, only this time, I'm going to have to erase the whole thing. That's a shame because that's a nice circle. Okay, this time we're going to use semicircles. Okay, so here's my circle. And we're still going to be perpendicular to the x-axis. Okay, so this time I am using semicircles, okay? So an area of a semicircle is 1/2 pi r squared. That's the area of the semicircle. All right, so let's figure out what the r value is. So my r value, this is r right here. Right, that's r, which is the y value. Okay, and we know that y is same as it was down there, right? I don't know why it doesn't let me highlight my writing. It's okay. So we have 1/2 pi r, which is the square root of 4 minus x squared. Right, that's r squared. So my area is 1/2, my area formula, 1/2 pi times 4 minus x squared. Okay? Okay, so our volume, we're still integrating from -2 to 2. And we're integrating 1/2 pi 4 minus x squared dx, which is, we're going to bring the 1/2 pi in out front, -2 to 2, 4 minus x squared dx. Okay, now I already calculated that in the previous problem, so I can save myself some time, right? The integral from -2 to 2 of 4 minus x squared dx is 32/3. So I don't have to redo that because I already figured that out. So this is going to be 1/2 pi times 32/3, which is 16/3 pi. Okay. Okay, let's keep going with this one. Let's see, part C. All right, see if I can get this out of here. Okay, get all that out of there. Okay. Okay, so this one we have an isosceles right triangle where the hypotenuse is the base. Okay, an isosceles right triangle where the hypotenuse is the base. All right. There's my right triangle. There's my hypotenuse, right? So that formula, that area formula, is 1/4 b squared. So once again, we have to figure out b, right? This is b here. Okay, similar to the square, right? This part right here, this part right here, that's going to be y. So my base is 2y, right? My base is 2y. So my base is 2 times y, which is the square root of 4 minus x squared. Okay, so my area formula is 1/4 2 times the square root of 4 minus x squared squared, right? So my volume is the integral from -2 to 2 of 1/4 2 square root of 4 minus x squared squared dx. Okay, and that comes out to be negative 2 to 2, 1/4 times 4 times 4 minus x squared dx. Well, the 1/4 and the 4 will cancel. So we're going from negative 2 to 2, 4 minus x squared dx, which we've done a couple times now, right? So that equals 32 over 3. Okay. Okay, same problem, only this time I'm using an isosceles right triangle where the leg is the base instead of the hypotenuse. So the area there is going to be 1/2 b squared. Okay, the base, we're still looking at the same situation where the base is going to be this full thing, which means it's 2y, right? So my base is 2 times the square root of 4 minus x squared, right? So figuring out the base, that's the key to the whole problem, right? Area equals 1/2 base squared. So 2 times the square root of 4 minus x squared squared. Okay, so our volume is going to be the integral from negative 2 to 2 of 1/2 times 2 square root of 4 minus x squared squared dx. Okay, which comes out to be the integral from negative 2 to 2 of 1/2 times 4 times 4 minus x squared dx, right? 1/2 times 4 is 2. I'm going to bring that 2 in front. And we get the integral from negative 2 to 2 of 4 minus x squared dx. Okay, we figured that out already, so we don't have to do the math again. So that's going to be 2 times 32 over 3, which is 64 over 3. Okay. Okay, keep going. Number 5. You'll start to get these. We do so many of them, you're going to get it. Okay, the volume of the solid whose base is bounded by the line x equals y squared, x equals 4. Okay, so first off, x equals 4. 1, 2, 3, 4. There we go, right there. Okay, x equals y squared. Well, to graph this, I need to make that y equals the square root of x. Okay, so that's going to be this curve here. Okay, it's going to look like that. Okay, cross sections are perpendicular to the x-axis and they're equilateral triangles. Okay, perpendicular to the x-axis. Here we are. Equilateral triangles. Okay. Okay. Area of an equilateral triangle is, area of an equilateral triangle is the square root of 3 over 4b squared. Okay, what's b? So here's my base right here. And this is my base. Okay, so once again, from the x-axis up to the curve, right, that's y, but I have to do that twice. So my base is 2y. All right, so the area is square root of 3 over 4, right? What's y? Y is the square root of x. So it's going to be 2 square root of x, right? Base is 2y squared. Okay, so we have our volume. We are integrating from 0 to 4. 0 to 4, square root of 3 over 4 times 2 square root of x squared dx, right? This is my b squared here, okay? Okay, so we can bring that square root of 3 over 4 outside. 0 to 4, 2 square root of x squared dx, right? Which gives us a square root of 3 over 4 times the integral from 0 to 4 of 4x dx, right? Bringing this 4 outside, square root of 3 over 4 times 4, so those 4's are going to cancel, right? So I'm just left with the square root of 3 times the integral from 0 to 4 of x dx, right? Which equals the square root of 3 times x squared over 2. Evaluate it from 0 to 4, which gives me, let's see here, that's going to give me square root of 3 times 16 over 2, which is 8 square root of 3. Okay? Let's keep going, let's keep going. Okie doke. Find the volume of the solid whose base is bounded by x equals y squared and x equals 4. Okay, I was going to skip this one, but we can't skip it. Okay, so let's see. We've got the same thing, right? Here's 4. And here's our curve, right? X equals y squared means that y equals the square root of x. Okay, we're perpendicular to the x-axis, so we want to solve for y. Okay, we are using triangles whose height is 1/4 the length of the base. Okay, so here's my base. Okay, so the area of a triangle is 1/2 the base times the height, but the height is 1/4 of the base, so that's 1/2 the base times 1/4 of the base, so that's going to be 1/8 b squared. And the base, okay, here's the base here. Here's my base. So again, I'm looking at from here to here is y, right? So my base is 2y, okay? So we're looking at 1/8 2y, or 2 square root of x squared, which equals 1/8 times 4x. All right, so my area that I'm going to use is going to be 1/2 x, right? So my volume is going from 0 to 4, 1/2 x dx. So that's 1/2 integral of x, from 0 to 4 of x dx. It's 1/2 x squared over 2, evaluated from 0 to 4, which comes out to 1/2 times 8, which is 4. Okay. Okay, next one's a little trickier. All right, we've got the same graph, the same curve, right? X equals 4. And x equals y squared, or y equals x squared, okay? We're perpendicular to the x-axis, but we're looking at trapezoids. Okay, so a trapezoid, the area of the trapezoid is 1/2 the height times base 1 plus base 2, okay? So if I were to sketch a trapezoid in here, all right, there's a base. Okay, there's a trapezoid, all right? Okay, the height is 2, all right? So this is going to be 1/2 times 2. And the upper base is half the length of the lower base, okay? All right, so first let's figure out the lower base. Okay. So this is the lower base. So there's y, right? So I need 2y, right? So the base is 2y, which equals 2. Oops, I wrote that wrong there. Okay, x equals y squared, so y equals the square root of x. Okay. So base is 2y, so it's 2 square root of x. Okay, so that's going to be base 1, square root, 2 square root of x. Plus base 2, which is half of that. So base 2 is just the square root of x. Okay, let me just double check myself now. 1/2 the height is 2. Okay, base 1, so from here to here is y, so I need 2y. Y is the square root of x, so it's 2 square root of x. Base 2 is half of that. Okay, so we're looking at 1, so that's just going to be 3 square root of x. Okay, so my volume is the integral from 0 to 4, 3 square root of x dx, which is 3 integral from 0 to 4 x to the 1/2 dx, which equals 3 x to the 3/2 divided by 3/2, right? But instead of saying divided by 3/2, we're going to multiply by 2/3. Okay, and that's going to be evaluated from 0 to 4. And that comes out to, let's see, 3 times 16 over 3, which is 16. Okay, let's look at the next one. Let the base of a solid be enclosed by the x-axis, the y-axis, and the graph of y equals 2 minus 1/2 x squared. Find the volume of each solid for the given cross sections taken perpendicular to the y-axis. Okay, so when we graph this, we're going to find that this is an upside down parabola, but it's bound by, okay, let me just do it this way. Let's see, it's an upside down parabola, and it's going to end up going like this, right? That's my upside down parabola, but it's enclosed by the x-axis and the y-axis. Oh, excuse me. perpendicular to the x-axis. Okay, I'm a little unclear on bound by the x and the y-axis. Okay, so I have to be talking about this area because it's the y-axis and the x-axis. If I included this, then the y-axis would not be containing it. Okay, all right, that's good. That's what I was a little unclear about. I had to think about that a minute. Okay, so we have that parabola, but we're only looking at this little quarter here. We're looking at that little quarter right there, okay? Now, it is perpendicular to the y-axis that we're talking about, so we need to rewrite this equation before we go too far, solving for x instead of y. So let me see, I've got 1/2 x squared plus y equals 2, so 1/2 x squared equals 2 minus y, right? Multiplying by 2, x squared equals 4 minus 2y. So we'll take the square root. So x equals the square root of 4 minus 2y. Okay? Okay. Did I do that right? Yeah, okay. Just checking my notes. All right, so now we're looking at squares, but the squares are perpendicular to the y-axis. So here's my square. Okay. Okay. So, oops, I gotta plug in my computer here. Okay, so let's see, we're looking at squares. So the area of a square is side square, or in this case, when we're talking about the volumes with cross section, we're talking about the base square. Okay, and the base of this square is the x distance, right? Different, it's the opposite of what the other one is. So we're looking at the x distance. So this is going to be the square root of 4 minus 2y squared. Okay, so our volume, we're going to integrate the square root of 4 minus 2y squared dy. Okay, so where are we going to integrate from? Well, it's with respect to y this time, so we're going from 0 to 2. That's where this curve crosses the y-axis, okay? If you don't remember how to do that, just remember the y-intercept is found by setting x equal to 0, right? So if this was 0, big 0 right there, y equals 2. The x-intercept is found by setting y equals 0. So then we would solve for x there, and we would get x equals 2 also. Okay, so in case you forgot that. Okay, so we're going from 0 to 2, right? So that's going to be from 0 to 2. When I square this, I just get 4 minus 2y dy. And that's going to give us 4y minus 2y squared over 2. So we'll just ignore those 2's there, right? So it's going to be 4y minus y squared, evaluated from 0 to 2. So that's going to be 8 minus, oh, what'd I do? Yeah, that's right. 8 minus 4, okay, minus, when I plug 0 in, I get 0. So this just equals 4. Okay. All right. Next one, we're going to do the same thing only this time we're going to use semicircles. Okay. Okay, so semicircles, and they are perpendicular with the y-axis. All right. Okay. The area of a semicircle is 1/2 pi r squared. So we have to figure out what r is, right? Okay, so r is basically 1/2 of x, right? So this whole thing here, this whole thing is x. So r is 1/2 of that, right? So r equals 1/2 x. So r equals 1/2 square root of 4 minus 2y. So our area is going to be 1/2 pi times 1/2 square root of 4 minus 2y squared. Okay, so our volume, again, we're going from 0 to 2. Okay, 1/2 pi times 1/2 square root of 4 minus 2y squared dy. Okay, so when I square that, I get v equals 0 to 2, 1/2 pi times 1/4 times 4 minus 2y dy. Okay, so we can take all these constants out of here. So volume equals 1/8 pi times the integral from 0 to 2 of 4 minus 2y dy. Now this integral part right here, we just did that over here. So I can just use that information instead of redoing it, right? So volume equals 1/8 pi times 4, or 1/2 pi. Okay, so you can get the idea here. We're doing the same thing. We just have to figure out the formula and the base. Once you do that, it's simple. Simple, simple. Okay, next one. So region R shown in the right is bounded by f of x and g of x. Find the volume of the solid form when cross sections are the shapes indicated below, perpendicular to the x-axis. Okay, so this top function is f of x, right? Bottom function is g of x. So the first one is a square. Okay, so here's my square here. Right. Okay, so there's my square cross section. Okay, so we're looking at area equals side squared or base squared, okay? So we need to figure out the base, so we need to figure out the length of this line right here, okay? Okay, so in order to do that, okay, so all we have to do is we have to take f of x minus g of x, right? That's the length of this side, right? The base. So our base is going to be f of x minus g of x. That's going to give us the length of that side. I'm just double checking myself here. Hold on a second. That's g of x. Oh, I want to go the other way around. Sorry. I guess it doesn't really matter because we'll be squaring it. So think of it this way, right? Way back when we were in Algebra 1, right? If you had x1 here and x2 here, right? To find the length of this line segment, we would do x2 minus x1, right? Or we could think of it in terms of y, because we're dealing with y, right? Here's y2, here's y1. To find the length of that line segment, we do y2 minus y1, right? It doesn't matter if the y, right? Let's say that y2 is down here and y1's up here. That's fine. Still doing y2 minus y1, okay? So it's the same idea, same concept. It's going to give us the length of that line segment, okay? Okay, so our base is going to be g of x minus f of x, okay? So this will be g of x, which is x cubed minus 4x. Did I switch them again? I did. I'm sorry, guys. I'm very sorry. I'm getting my g of x and f of x mixed up. Let me label them a little more clearly, right? This is f of x. This is g of x down here. Okay, so we are looking at f of x minus g of x, which is what I said initially, right? So this is going to be sine pi over 2x minus x cubed minus 4x, right? That's our b squared, okay? So our volume is going to equal the integral, right? I'm going from, it's perpendicular to the x-axis, so we're looking at in terms of x, from 0 to 2. And we're going to do sine of pi over 2x minus, I'm just going to distribute that negative, x cubed plus 4x squared dx. This is a calculator section, so we're just going to put that in our calculator, and we get that the volume equals 16.9446. Or you could round it to 16.945 if you want to, okay? Okay. The next one is a semicircle. Right? Once we figure out the first one, the others are easy. Okay, semicircle. Right? Area equals 1/2 pi r squared. So we have to figure out r. Okay. So f of x minus g of x is the base or the diameter, right? F of x minus g of x. So r is 1/2 of f of x minus g of x. So r equals 1/2 of sine pi over 2x minus x cubed plus 4x. All right, that's r. So my area is 1/2 pi, and we're going to do square r, so that's going to be 1/4 sine pi over 2x minus x cubed plus 4x squared. Okay, that's my r squared. So our volume, we're going to integrate. So I'm going to bring that 1/2, 1/8 pi times 1/4. So 1/8 pi, bring it outside, from 0 to 2. And then we have sine pi over 2x minus x cubed plus 4x squared dx, which is really the same thing that we had over here. So we just take that and multiply it by 1/8 pi, and we get 6.654. Okay. So just to recap that, I had to find the radius. So this f of x minus g of x, that is basically your diameter. So we take half of that. That's my radius. Then I had to square it.
In the refrigerator, there's a container there.
Okay, let's do it again with equilateral triangles. Okay. All right, so equilateral triangle. Here we go. Okay, so the formula for our equilateral triangle, that's the square root of 3 over 4 times the base squared, right? Square root of 3 over 4 times the base squared, all right? So the base, is the f of x minus g of x, right? So, yeah, base squared is right here. We already did that work, right? So here we're looking at the volume going from 0 to 2. Sorry, I get distracted. Square root of 3 over 4 times the base squared, which we already figured out, is sine pi over 2x minus x cubed plus 4x squared dx. Okay, and that's going to be the square root of 3 over 4 times the integral from 0 to 2 of sine pi over 2x minus x cubed plus 4x squared dx, which comes out to, so it'll be square root of 3 over 4 times this number, right? 16.9446, which comes out to 7.337. I guess I should double check that, huh? Let's see. Yeah, okay. Okay, isosceles right triangle. So we're just doing the same thing over and over and over and over and over again, right? Isosceles right triangle, the area for that is area equals 1/2 base squared. Okay, so here we get the same thing. So the volume equals integral from 0 to 2. I'm going to just put that 1/2 in front, right? And the base again, sine pi over 2x minus x cubed plus 4x squared dx. And that equals 8.472. Okay, got to find the area formula, and then we have to figure out the base. Okay, Okay, number 14. This time we've got a rectangle with a height of 3. All right, a little bit different now. Rectangle with a height of 3. Okay. So rectangle is going to be the base, right, which we figured out, times 3. Okay. So we're looking at area equals sine of pi over 2x minus x cubed plus 4x times 3. Okay, so our volume is the integral from 0 to 2 of this. So I'm going to bring that 3 in front. And this will be sine pi over 2x minus x cubed plus 4x dx. And remember, we're using our calculator on this. This is a calculator section. So this comes out to 15.8197. Okay, number 15, a rectangle with a height equal to twice the base, okay? So again, we've got our base, right? So it's going to be the sine pi over 2x minus x cubed plus 4x, that's our base, right? Times the height. Now the height is twice the base, so it can be times 2 times sine pi over 2x minus x cubed plus 4x, right? So there's my base, and then this is the height, okay? So my area is going to be 2 times sine pi over 2x minus x cubed plus 4x squared. So my volume, going from 0 to 2, I'm going to bring that constant in front, right? And we've got sine pi over 2x minus x cubed plus 4x squared dx, right? When you have problems like this, you can save yourself some time because we've done that part so many times. The integral from 0 to 2 of that f of x minus g of x squared is 16.9446, right? So this is 2 times 16.9446, which comes out to 33.889. Okay, you can save yourself a lot of time. Okay. Okay, number 16. The volume of the solid whose base is bounded by, okay, we've got x equals 0, y equals 0, so that's the x and the y-axis, right? This is a linear function with the indicated cross-section perpendicular to the y-axis. Okay, so graphing this, I'm going to use the x and y-intercept method. So x is going to cross the x-axis at 6. Okay, 1, 2, 3, 4, 5, 6. And it's going to cross the y-axis at 3. 1, 2, 3. Okay, just kind of draw that in there. Okay, so we're perpendicular to the y-axis. So we have squares that are perpendicular to the y-axis. So that means I need to rewrite this. Oh, this equation is written correctly. Oh, good. Okay. Okay. So I've got squares perpendicular to the y-axis, so my squares are going like that, right? Okay, so the area of a square is going to be the base squared, and the base is equal to x, right? So that's going to be 6 minus 2y squared. Okay, now we're integrating with respect to y. So that means I'm going from 0 to 3. 0 to 3, 6 minus 2y squared dy. So I will expand that out, 0 to 3, and that's going to be 36 minus 24y plus 4y squared. Okay, and when we integrate that, we get that the volume equals 36. I keep making messy zeros there, huh? Okay. Number 17, we're looking at quarter circles. All right. Quarter circles. So we're looking at something like this. Okay, a bunch of quarter circles like that. All right, so the area of a quarter circle would be 1/4 pi r squared. And in this case, the r, okay, let's figure out what the r is, see if we can get a handle on that. All right, this is a quarter circle. So if it was a full circle, it would be like that, right? So this little piece right here, this is r. Okay, so r is actually x, the x distance, okay? So my area is going to be 1/4 pi, and then we have 6 minus 2y, that's x, right, squared. 1/4 pi r squared. All right, so my volume, I'm going to bring the 1/4 pi outside the integral. We're going from 0 to 3, because it's with respect to y. 6 minus 2y squared dy. Now remember, we already did that. Integral 6 minus 2y squared dy, right? So this is going to be 1/4 pi times 36, which equals 9 pi, right? Don't do the work over and over again. We already did it once. Okay. Okay, last one. This one's a little bit different, okay? So we have two functions, f of x and g of x, right? So this is the 1 minus cosine here, and this one is e to the negative x squared, okay? Find the volume of the solid formed whose cross sections are quarter circles that are perpendicular to the y-axis. Okay. I'm sorry, perpendicular to the x-axis. All right, so again, we're looking at quarter circles. Okay. All right. So we're looking at something like this, right? Oops. Okay. Something like that, okay? All right, so we're looking at the area equals 1/4 pi r squared. And again, in this case, r is actually this entire thing. So how do I get that, right? So what function's on top? That's going to be f of x, right? So r is equal to f of x minus g of x. Okay. Okay. So we're looking at a volume. Oh, they're kind of stepping us through it here. And find the points of intersection for the figure. Okay, so this is a calculator section. So my points of intersection here and here are at x equals, I'm not going to pull my calculator up. I know you know how to do that. x equals negative 0.941944, and at x equals positive 0.941944. Okay. Now I am integrating with regards to x, so I just need the x value. All right, write the integral. So we're looking at volume equals, right? So we needed those points of intersection so that I know what my lower and upper bounds on the integral are. So we're going to go from negative 0.941944 to positive 0.941944. Okay, the area function, so that's going to be 1/4 pi r squared, right? We just said r is f of x minus g of x. So that's going to be f of x is e to the negative x squared minus g of x, so 1 minus cosine x, right? And that is squared, pi r squared, all right? So that will be 1/4 pi times the integral negative 0.941944 to positive 0.941944, and that is e negative x squared. I'm going to distribute that negative, minus 1 plus cosine x squared dx, okay? And this is a calculator section, so we will just put that in our calculator, and we get the volume equals 0.724. So what made this one different is that, well, first off, we had to subtract the curves, right, to get this base. But then we also had to figure out where they intersected. Okay. Okay, so we did a lot. Hopefully by the time we got through them, hopefully you're feeling like you have somewhat of a grasp, okay? This is one major topic. I'm going to continue making these videos to cover some more volume and then just some miscellaneous things. But volume is the one big topic that we have not had opportunity to touch on. Okay.